I didn't want
All right, is everybody ready? As ready as you're going to get? All right, first thing I want to do is correct a mislabeling I had on this picture. That shouldn't be alpha beta, that should be alpha alpha or. That should be all one unit. And that was drawing real quick. Right, the heme group lives within one subunit. So that's all one alpha unit or it's all one beta unit. The heme group is in one unit, and I was thinking too fast and I meant alpha or beta.
Perfect.
Yep, so like this whole thing, like if we look back at one of our older pictures. Right, here is my heme group within a beta, and here's my heme group within an alpha. Yeah?
It says 2 alpha subunits, does that mean 2 alpha helices, or does that just mean it's just like a name for a unit? Does it mean that hemoglobin has 2 alpha helices and
No.
2 beta chains?
No, just has to be the way they chose to name it. That there are 2 groups that look the same, they're called alphas, and there are 2 domains that look the same, they're called betas. Yeah, yeah. Yeah?
Julie and I were saying last night, we're confused with the terminology between domain and subunit.
Mhm.
I feel like that's what they use.
They are used fairly interchangeably, yes.
Like there was one problem where it looked like a domain was within the subunit, and then another way it was described as a subunit was a domain.
Yeah, so a domain is the quaternary unit, and so it's also that quaternary structure. So in this case, I have 4 subunits, which are the same thing as saying 4 domains. Yeah. In this case, the 4 subunits are different polypeptide chains. It could be in theory that your domain is all part of the same chain. It's just like one's all alpha helixes and one's all beta sheets or something like that. So all domains are subunits, but not all subunits are domains. Yeah?
You say all domains are subunits, but not all subunits.
Yes. That one. That should have been all alphas or all betas. That should be. Does that make sense, Victoria? And that's why I was looking at this one. Because I'm looking at one big beta unit, and a beta unit has one heme in it, or an alpha has a heme in it. So this is my heme, and it's all within an alpha or a beta. Yeah, with the colors, it's helpful. So. All right, in that case, let's finish discussing hemoglobin. This is where we left off on Monday, talking about the relative stability of T and R states. All right, when I was at low partial pressure, I'm mostly T. When I'm at high partial pressure, I'm mostly R. Where T is my no oxygen, R is my fully oxygenated hemoglobin. So, looking at this hemoglobin curve, this sigmoidal hemoglobin curve, So lungs have a partial pressure around 30 torr. And your tissues, like your fingers, your extremities, have a partial pressure closer to 10. Somewhere in that range. So why is it good that you're in the R state at the lung partial pressure? Right? The lungs is where it picks up the oxygen. So you want to have most of your hemoglobin in the R state, oxygenated, at that partial pressure. Okay, so we head out to your fingers at 10 torr. What happens to my hemoglobin? It drops off all its oxygen. So at 10 torr, the preferred state is deoxygenated. It prefers to drop off all the oxygen. So the hemoglobin is designed so that high pressure, it prefers to be oxygenated. At low pressure, it prefers to be deoxygenated. So it picks up in the lungs, drops off in the tissues, which is good because that's how it works, up in the lungs, out in the tissues. And then it floats back to the lungs and can be reoxygenated. Flipping back way farther, this is myoglobin. Right, myoglobin had just this regular kind of curve. If we look at the same zone, lungs and tissue, why is myoglobin not good as your main oxygen transporter? It's still really high. The percentage of oxygen that's going to release is not very much. We're looking at this point versus that point, which is what we calculated over here. That you've released very little oxygen to your tissues. That's mostly all still oxygenated. But in this case, I'm going from almost 1 to almost 0 in my YO2. So it's a better transporter for oxygen. Okay? Then let's talk about how pH affects all that. So the effect of pH on hemoglobin transport. As a fun fact, turns out that the pH in your lungs is 7.6, and the pH in your blood is about 7.2. So which one of those two is more acidic? Okay, so the blood pH is more acidic, comparatively. I don't think these are the right units. I don't think that should be torr. Anyway. So looking at these, this is a hemoglobin binding curve. How do I know it's a hemoglobin binding curve? It's a little S-y, right? It has a little bit of an S shape to it. So the affinity of hemoglobin for oxygen, like we looked at in that previous picture, all right, so just restating what we all agreed to, that the affinity of hemoglobin for oxygen is higher in the lungs and lower in the tissue based on its partial oxygen pressure. Well, there is also a pH effect on hemoglobin's binding ability. So if I look at pH 7.6, which is my lung pH, and I look at somewhere here, we'll say 60, somewhere in the middle. At pH 7.6, which is the lungs, comparatively to 7.2, does it have a higher or lower binding affinity? at 60 torr, is pH 7.6 a higher or lower binding affinity? Higher, right? Here's my 7.6. Here's my 7.2. Right? So at the same pressure, imagining that your whole body's at one pressure, higher pH means higher binding affinity, so less acidic. So higher pH, greater bonding affinity for oxygen. What about at lower pH? So imagining that we're up here at the lungs, pH 60, 100, somewhere in there, and we're at 7.6, much higher binding affinity. What if I'm now down in the tissue at 20 or 30 torr and lower pH? Do you want a high binding affinity in your tissues or a low binding affinity in your tissues? Low binding, right? You want to be dropping it off. So you want the lower pH, lower binding affinity. So there's two things really working for hemoglobin in its favor. That at higher pressures is more likely to bind oxygen, and higher pHs is more likely to bind oxygen, which is good. Those are both true in the lungs. Then your tissues, your extremities, it is a lower pH and lower pressure, which means it's more likely to want to drop off the oxygen. So both are advantages. So you may be thinking, I know you're not actually thinking this, but once I ask it, you'll be like, oh yeah, I was wondering that. Why does pH have any effect on this? Why does pH have any effect on this? So, if I write up here, can everybody still see the notes at the bottom? Right at the top, okay. Bless you. So the conformational change, which is what kind of conformational change? Mechanical. It's a mechanical shift, right? The conformational change is a mechanical shift from a T to R state alters the microenvironments around the amino acids. So that picture we looked at the other day where I'll just go ahead and find it because you guys have no idea what I'm doing when I just do that. I know what I'm talking about. I'm sure you guys will be like, oh yeah, that picture. Let's see if I can find it. This one. Right, with our hydrogen binding and our oxygen, there's a mechanical shift in the two that, in this case, the alpha-beta channel shifts, right, and was a hydrogen bond there, and now it's a hydrogen bond up here. So that change, that mechanical shift in that area is obviously affecting the amino acids in that channel. And it's going to cause a change in pH in that channel. So, I'll wait till everyone's done because I need to flip the page over because I got one more sentence that I don't think will fit in there. Okay. So let's imagine that this is what state is my hemoglobin in if it is not bound to the oxygen? Two different answers I'll take. There's a letter and T state, otherwise known as the deoxy state. All right, so I'm in my T state. There's some free oxygen floating around. In that case, I am in equilibrium. That's my other state. What's this one called? R, or the oxygenated state. If oxygen has now bound to hemoglobin, what must be the other product? My little hydrogen proton floating around out there. So the binding of oxygen causes protons to be released. If the protons are being released, what is that doing to my proton concentration in that area? Increasing, decreasing? If it's increasing the proton concentration, is that more acidic or less acidic? More acidic. So, all right, so the binding of oxygen causes the solution around the hemoglobin to become more acidic. Which, what did we just say about the lungs? Are the lungs more or less acidic than the tissue? You can flip back and look at your picture. Right. So that binding causes the solution to be more acidic, which, when these are released, more acidic. Let's see. Lost my train of thought. More acidic. Because we're in equilibrium, when these protons are released and the solution becomes more acidic, it's going to push the reaction back to the left and cause the oxygen to be released. Does that make sense? So I bind oxygen, the solution around it becomes more acidic because you're out in the tissues at this point. So then it's going to force it back to the left to release the oxygen so the hemoglobin gets its proton back. Some Le Chateliers again, right? So then the opposite would be true. Ask away. Yeah.
So if you're binding the oxygen in the lungs, that's where it starts to become more acidic. So it waits till it moves to the tissues to be released.
I guess the key phrase in this is that's a microenvironment. It's not the solution around the hemoglobin. It's the solution in those little tiny channels.
So why doesn't it release it once the oxygen binds? It's creating more hydrogen.
Right, because while it's in equilibrium, it's not a fast equilibrium, right? It's the difference between like equilibrium kinetics. That while it's true that when it binds the oxygen, it releases a proton, it is not a fast reaction to go back this way. So
Once it gets to the tissues, then it's at that more acidic pH where it'll release it.
Yep.
The tissues are more acidic than the lungs.
Yes, yes. So it's a combination of factors. It's going to be the kinetics of the reaction, the pH of the solution, and the pressure. So all three of them have to work together. So that's up in the lungs and out in the fingertips. Yeah, that's a good question. So, all of these factors combined together the effective pressure, the pH, and the equilibrium reaction of hemoglobin and oxygen combining or not combining. Or altogether called the Bohr effect. In any other class, have you talked about respiration, like actual lung respiration, not cellular respiration? No. Anatomy, maybe a little bit? Okay. Oh, which way am I going? I'll just put the whole thing right back here until you guys are done. I don't want to rush everybody. Is the anticipation getting to you? Ready? Ready? Okay. All right, this is another great time. If you have any kind of colored, you're going to need a red and the blue. All right, so the Bohr effect is how we describe actual respiration in your body. And it's the effect of, right, you breathe in oxygen, what do you guys breathe out? Carbon dioxide. What is the acidic form of carbon dioxide? Carbonic acid. And so all these together combine to produce the Bohr effect. This picture's in your textbook also, so if you don't have colored things, that is okay. You can look in your textbook later. All right, so just some reminders down here before we get started. Okay, so the Bohr effect is needed for oxygen transportation. That is how our oxygen gets from your lungs out to your muscles. So here in your lungs, we're going to start on the inhale part of it. So the lungs is where hemoglobin is going to be red. Okay. So in the lungs, the oxygen pressure is high. Which means the oxygen concentration, either way you want to think about it, oxygen pressure, oxygen concentration, both true. Right, so if we're at high pressure, the hemoglobin is going to preferentially bind the oxygen, go into the R state. So my hemoglobin has now bound oxygen coming in from the lungs, which means that it has released that proton that it had, right? Hb plus has now released that proton. Far so good? Okay. In this diagram, that proton now appears up here. So when the hemoglobin binds to the oxygen, it releases the proton, which is now available to do some other work. Does anyone recognize what that molecule is? Carbonate or carbonic acid. Both, yeah. So that proton is now going to combine with this HCO3 minus. In the presence of this enzyme, this is an enzyme right here. I have HCO3 and a proton. I'm going to release water to do other things. And it leaves me with carbon dioxide, which then you breathe out. So the only reason you're breathing out carbon dioxide is because that proton has been released from the hemoglobin to be available to produce carbon dioxide to breathe out. So you're thinking, where does this carbonic acid come from? Let me finish this sentence first. So in the presence of carbonic anhydrase forms CO2 gas, which is breathed out. So where does that HCO3 minus come from in the first place to be available to react with that proton to make carbon dioxide your final product? Well, as we follow our hemoglobin going this way, right, it's now been transported all the way to the muscles, where it's going to drop off its oxygen. So this oxygen is now being deposited over here. To be more appropriate, it's kind of purpley, so it's kind of reddish, bluish. Right, hemoglobin in its deoxygenated state is really more purple, it's not really blue. But if you're looking at your skin, the blue ones are your T-state hemoglobins headed back to your lungs. In case you're curious, that's why it's blue, because they're out of oxygen and they're headed from your fingers back to your lungs to go refuel. The red veins aren't as easy to see, but especially in your fingers, because it's mostly headed back to the lungs. But if you could, that's why when you cut yourself, it comes out red because there's all this oxygen at high pressure on the outside, so it instantly becomes in the R state. So, fun fact, that you can't actually bleed out blue. All right, so now I have oxygen, and this is, anyone guess what MB stands for? Myoglobin, right? This is the myoglobin that's available in your muscles and extremities. That's going to bind the oxygen. And respiration, this is on the cellular level, like providing oxygen to your cells to do work, which we'll get into a discussion about lactic acid later. But this is where the oxygen for those lactic acid reactions come from. All right, so now I have my free oxygen, which is going to be consumed, all right, at the top here. I'm going to say that tissues consume oxygen through respiration. All right, so now respiration has occurred. I now have two products. I have carbon dioxide and water left over from that reaction. That carbon dioxide is going to also travel out of the muscles and it's going to start heading back towards the lungs. But carbon dioxide as a gas doesn't travel real well. So we have to change it into a different form for it to be able to be mobile to get back out to the lungs. Fair enough, right? Just like oxygen doesn't travel by itself, carbon dioxide can't travel by itself. It has to be in a different form. So we're going to use the same enzyme we had before, carbonic anhydrase, and use this water. So over here I produced water and kicked out carbon dioxide. This time I'm going to put in carbon dioxide and water to make my carbonic acid. So that dissolved carbon dioxide is going to react with water in the presence of that same carbonic anhydrase to make my carbonic acid. Which, when it does that, what's the other product it made? It made a proton. Where does that proton need to go? Down to this hemoglobin so that it can travel back to the lungs. Because, right, this hemoglobin just dropped off its oxygen, so now it's in like a weird in-between state, so it needs to grab the proton that was just released by the production of my carbonic acid to then be in the protonated form to head back to the lungs. So it's really two cycles, right? This bottom cycle interacting with this top cycle in order for the oxygen to get in and the carbon dioxide to get out. It's pretty neat, actually, that all those things go on. How often do you breathe in a minute? I don't know, like 40 times. And all this is going on 1,000,000 times for every one breath. Pretty crazy. What do you think about it, that all that works? Yes, Sarah?
You said the proton, the byproduct, like, what does it do after it's made?
This one?
Yeah.
When this, so it makes H3O and H+. Right, those are the two things that get made there. So that H+ now binds to the hemoglobin that had just dropped off its oxygen. It's reality. It's neat. That works all the time. Almost no one has a Bohr deficiency that you're not breathing in oxygen, pushing out carbon dioxide. That's pretty really mind-blowingly fantastic. Any other thoughts on the Bohr effect and how amazing breathing is? Next time you start breathing, hyperventilating, we'll get to a discussion about hyperventilation. Or traveling up in the mountains. So that's another fascinating discussion about now your lungs are, like your whole body's at a different pressure, and so you're not able to make this cycle as well, and so then you try and make up for it by hyperventilating, which then causes all kinds of issues because you're not breathing in as much oxygen as you're pushing out carbon dioxide, and then you pass out. So
Is this all still in the test?
this and this very last thing about 2,3-BPG, and then everything else in that chapter is not. Structural proteins, I guess. We're just going to, the 2 globins will be on there. Then let's talk about 2,3-BPG. So 2,3-bisphosphoglycerate has a structure that looks like this. So red blood cells, the cells that contain your hemoglobin, use this BPG to fine-tune the hemoglobin function. Bless you, bless you, bless you. So, looking at my graph, because you know I'm real passionate about graphs. What is the difference? Let's just pick we'll pick 20. At 20 torr, what is the difference in binding without and with? Which one is able to bind with higher affinity? Without binds at higher affinity than at 20. Okay? So at this point, okay? So you can see from my little graph here that 2,3-BPG reduces the pressure required to bind oxygen, right? It lowers the whole curve. And how it goes about doing that is how many charges does 2,3-BPG carry on it? -2, -2, -1, 5, right? Overall has a net charge net charge of -5. So, looking back at our heme group, let's see if I can find a picture of that real quick. All right, so here's my heme group, where there's 1, 2, 3, 4, 5 nitrogens surrounding this iron +2. What 2,3-BPG can do, because it has a net charge of -5, so 2,3-BPG binds in the cavity where oxygen typically binds and keeps hemoglobin in the T form. Which is what we're seeing on this graph, right? At 20, we're pretty high up, which would typically be the R form, but with 2,3-BPG, I can stay in the T form at higher pressures than I would typically. Right, because up here, we're past half, so you're probably more R than you are down here. So, it keeps hemoglobin in the T form. Why would you want hemoglobin to stay in the T form longer? Excellent question. Babies. Babies in their growing state. Feti, fetuses, many feti, whatever it is. Growing babies take advantage of this effect to obtain oxygen through the umbilical cord. So it turns out that babies in the fetus state, I don't know exactly how to say that exactly right. Anyway, growing babies don't have alpha-2, beta-2 hemoglobin yet. I'm going to write some of these other things on the back. So, right, adult hemoglobin's alpha 2, beta 2, there's 2 alphas, 2 betas. It is not that. It has the same alpha structure, but it doesn't have betas as the other subunits. It has gammas, which are similar, but an important difference. They don't have that distal histidine that's holding the iron from the backside. It doesn't have histidine in that spot. Quick, before Friday, what does SER stand for? Polar, nonpolar, charged, hydrophobic, hydrophilic. It is nonpolar. What about histidine? Polar, nonpolar. It is polar. So we have switched out a polar amino acid for a nonpolar amino acid. Big deal. That's a huge, huge deal. Because the histidine has a positive charge that's able to hold on to the ring pretty well. This is polar. This one's nonpolar. Yep. Serine, no charge. Dramatically affects that binding ability. So fetal hemoglobin needs that 2,3-BPG in the binding cavity to keep it in the T state longer to allow oxygen to bind. So allow it to bind at lower, at different pressure. I guess not lower, different. Yeah. Sorry, I meant charged. This is positively charged. This has 0 charge. Yeah, charged. Histidine will be positively charged at that pH, typically pH 7-ish. Histidine is positive charge. Serine at pH 7-ish is 0. So not polar in that it's not charged at that particular pH. Seven-ish. So you need to have the 2,3-BPG in there to hold it into the T state to allow it to have enough time to get the oxygen out of the umbilical cord bloodstream to then get into the R state and take it to the fetus. So babies typically have this type of hemoglobin until they're about 6 months old, at which point they've slowly converted all of this over to this, which is, again, fascinating that it's able to, it knows kind of how old it is, and is able to stop making this and start making that. Just mind, all these things, just blow my mind. So, questions about our 2,3-BPG?
Is it like a gradual transition?
It is. Yep. So when the babies are born, they have all this, and by the time they're 6 months old, they're all, I guess, adult hemoglobin. Pretty neat. All right, I got one more fun fact. Yes, there are some deficiencies if they're not able to convert it over, that they're not able to transport oxygen as well, because now they're outside, and so the pressure is more like an adult pressure, 30 and 100, where inside the pressure is shifted to kind of higher pressures. So,
What kind of deficiencies, like, how can it affect them?
they're not able to transport oxygen as well. So when they breathe in, even though they're breathing in the right amount of oxygen, like they're not getting the oxygen all the way out to their extremities. And so it's like tissue death and things like that. Yeah, it'd be. Sickle cell's my next thing.
So is that the
This is the last fact. Yeah, this is the end of the test for Wednesday, just last fact about hemoglobin. The other thing that can go crazy with your hemoglobin is sickle cell anemia. And this is a chain, is a primary chain issue. So, right, our deoxyhemoglobin, I don't know why that should be hemoglobins, I don't know why the S got big. And deoxyhemoglobins form insoluble filaments that deform in red blood cells, because instead of being like individual cells that can smoothly run past each other, they have this weird sickle thing to them. And then they start catching each other. So they're not sliding past each other in the cells anymore, or in the bloodstream. They catch each other with, like, they have an elbow sticking out. And these rigid cells cannot pass through the capillaries because they're stuck to each other, and they start to kind of clot almost. They clot inside the... And so, again, tissue death because your extremities aren't getting the oxygen that they need because you have a clot somewhere in your vein. And it all becomes... We have switched out one amino acid in our primary chain. We have valine in there instead of glycine in the beta chains only. So that one change in the primary structure causes death, pretty much. Which is pretty, again, the fact that there's a very small percentage of the actual world population that has this issue, this primary chain issue, is, again, pretty crazy that everybody's been able to successfully make your primary chains to fold them up into quaternary subunits, that everybody's subunits are working right. So your body's an amazing machine, an amazing machine. All right, that's the end of the things for tests. I have your quizzes to get back to you.